stable materials can exist in three states or phases, which we call solid, liquid, and gas. The relations among these phases and the transitions between them are called phase behavior. Most of the representations of these phases, which occur in textbooks, models, graphs, and here, are for equilibrium states, states in which there is no net change with time of any of the properties of the system. However, we are principally interested in the changes in these phases, both in industrial and in biological and geological situations. Here we will see these phases in the process of change. Any change requires a non-equilibrium condition. However, if we make the changes slowly enough, we will pass through states which are practically equilibrium states. Such very slow changes are called quasi-static processes. These states are normally described in terms of three readily measurable parameters: the pressure, the temperature, and the specific volume. If we label the three coordinate axes of a solid as pressure, temperature, and specific volume, then it can be shown that any possible state of a system is represented by some point in this space. All of the observable equilibrium states are represented by a single surface, which is shown on this model. Any point which is not on this surface represents a point which is not observed in nature. This model extends to infinity in these three directions. Only the corner nearest the origin is shown. Most of the interesting phenomena occur in this corner. This simple surface representation is only possible for a simple homogeneous substance. On this model are shown the solid, liquid, and gas states of a substance, as well as the transition regions in which a gas and a liquid, a gas and a solid, and a liquid and a solid are present. Also shown are the critical point and the triple point. Although the three-dimensional model is the most convenient way to visualize all the relations among the phases, for practical numerical work, its three-plane projections are more convenient. These are the pressure-temperature projection, shown here on the model and here in graphical form. The pressure-volume projection, shown here on the model and here in graphical form, and the temperature-volume projection, shown here on the model and here in graphical form. In order to have a model in which all of the important parts are visible, it is necessary to use a distorted scale which stretches out the low volume and low pressure corner of the model. To see this, look at the pressure volume diagram obtained from the model and the pressure volume diagram for a typical substance. In order to see this material in this corner, it is necessary to expand that corner 10,000 times. Thus, although the model is useful for grasping relationships, it is not typical of real numerical values. Many of the interesting phase changes occur at pressures much higher than atmospheric, and therefore it is difficult to observe these changes in ordinary laboratory equipment. To observe these changes visually, we will use the high-pressure visual observation equipment used for earth science research at the La Habra laboratories of the Chevron Oilfield Research Company. The principal piece of apparatus we will use is a high-pressure, windowed equilibrium cell. The outside is an insulating container. Inside is a large block of stainless steel about 4 inches thick. A 1-inch wide slot has been cut in this block, and both sides of this slot are covered with thick, high-strength glass windows held in place by bolted retainer plates. The temperature of the block and of its contents is controlled by regulating the temperature of the air, which is circulated around the block inside its insulating container. The air can be heated with ordinary electric heaters or cooled by introducing liquid nitrogen into the circulating air stream. The sample under investigation is held in the slot between the glass windows. In the slot below the sample is mercury. The volume of the sample can be changed by increasing or decreasing the amount of mercury with a positive displacement pump. Normally, the sample is viewed in this mirror through the side of the enclosure. This is a safety measure. If the glass window breaks when the cell contains a high-pressure sample, the fragments will fly out away from the observer, who is looking on at right angles through the mirror. Behind the sample, on the other side of the block, are lights to illuminate the sample. We have added a piece of yellow cardboard, which makes observation of the phenomena easier. Most of the samples you will see here are colorless and transparent. We found them easiest to observe against this yellow background. We are all used to the idea that lowering the pressure on a liquid can cause it to boil. Most of us are familiar with the reverse idea that raising the pressure on a gas can cause it to condense. This occurs in most household refrigerators. If we compress a gas at constant temperature, its pressure will rise until a liquid begins to form. During continued compression, all the gas turns to a liquid and the pressure remains constant. When all the gas is condensed, further compression of the liquid results in a very rapid rise in pressure. Here is a sample of ethane contained in the equilibrium cell on the left side of the picture. On the right are a temperature indicator, which senses the temperature of the block around the sample via a thermocouple, a clock whose motion will show how much we have slowed the action in order to have quasi-equilibrium states, and a pressure gauge, which is connected to the mercury below the sample and shows the pressure on the sample. We now compress this sample of ethane at constant temperature of 80 degrees Fahrenheit. Notice the accelerated motion of the clock, which indicates how slowly we must proceed to keep at quasi-equilibrium states. The pressure rises first. Then liquid begins to appear and the pressure remains constant during the entire time that the gas is condensing to form the liquid. When the last gas disappears, the pressure rises rapidly as we continue to decrease the volume. This process looks this way on the model and this way on the pressure temperature diagram, this way on the pressure volume diagram, and this way on the temperature volume diagram. We are also used to the idea that heating at constant pressure causes transition from liquid to gas, normally by boiling. However, if we heat at constant volume, the results may be somewhat different. In constant pressure heating and boiling, the liquid expands while changing to a gas and drives back the atmosphere. If the gas cannot escape, then it will cause the pressure to rise. If the volume is large enough for all the matter present to exist in the gas phase, then heating at constant volume will change a gas-liquid mixture into an all-gas system, as is shown in the constant volume heating of this mixture of gaseous and liquid ethane from 80 to 100 degrees Fahrenheit.
This process looks this way on the model, and this way on the pressure temperature diagram, this way on the pressure volume diagram, and this way on the temperature volume diagram.
If, on the other hand, there is less gas present initially, then heating will cause the gas to disappear. Here we see a gas-liquid mixture of ethane, also being heated from 80 to 100 degrees Fahrenheit, but with less gas initially. The liquid expands, just as the liquid in a thermometer expands, and finally fills the volume, causing all the gas to condense into it.
This process looks this way on the model, and this way on the pressure temperature diagram, this way on the pressure volume diagram, and this way on the temperature volume diagram.
The most interesting situation is the intermediate between the last two, where the volume is chosen as the critical volume. In this situation, as we heat the mixture, the pressure rises, so the gas becomes more dense. Its specific volume decreases. Simultaneously, the temperature rises, so the liquid expands. Its specific volume becomes greater. When the two become the same, we have reached the critical point, and all distinction between the two phases vanishes. This is visually observed by the disappearance of the surface of separation between the two phases. Here we see this happening when we heat ethane at constant volume through its critical temperature, 90 degrees Fahrenheit. The surface of separation does not disappear with a bang, but merely fades away. As we approach this point, all of the measurable physical properties of the gas and liquid become more alike until, at the point where the surface vanishes, the liquid and gas become identical. This point, at which the liquid and gas become identical, is an easily reproduced point for any pure substance. It is called the critical point. The temperature, pressure, and volume corresponding to this point are called the critical temperature, critical pressure, and critical volume. When a substance exists at a temperature greater than its critical temperature, it can be compressed from the large specific volume corresponding to a gas to the small specific volume corresponding to a liquid without any visible surface of separation appearing. When a substance exists in this state, it is spoken of neither as a gas nor as a liquid, but as a dense fluid. A more dramatic view of what occurs at the critical state can be seen by cooling a dense fluid at its critical volume from a temperature above the critical temperature to one below it. Here we see this with ethane. The fluid turns reddish, then a cloud forms which blocks the light, then droplets appear and separate, forming the gas and liquid phases. Here we see the same process, not in accelerated motion, but in real time. As the temperature is lowered, a state is reached at which the dense fluid can reorganize into a gas and a liquid. However, it must form the close molecular associations in the liquid state. This begins as it forms molecular clusters throughout the entire dense phase. These clusters cause the red color. Then the clusters grow to the size of fog particles which block the light. Finally, the fog particles grow to the size of droplets and settle to the bottom of the cell, forming a liquid and leaving the gas behind. One can also observe the critical phenomena by compressing a mixture which is at its critical volume and slightly below its critical temperature very quickly. The path which is followed is practically an adiabatic path, like this. Adiabatic compression raises the temperature slightly, and here we can see the surface of separation disappearing in real time. Notice the intense convection current at the top of the cell as the surface of separation is disappearing. The dense phase there is hotter than the surrounding metal and hence giving up heat to it rapidly. If we repeat the same sequence but do not compress quite so far, we see the surface of separation disappear. Then, as the dense phase near the former location of this surface begins to cool, we see the red color of the critical state, followed by fog formation as the system reverts to a gas-liquid system at the temperature of the metal walls of the cell. From this discussion, it is clear that we can make the transition from liquid to gas without ever seeing an interface between gas and liquid. This is called the circumnavigation of the critical state. Here we have a gas-liquid mixture of ethane at a specific volume less than its critical volume. It is being heated from 80 to 100 degrees Fahrenheit, and as you can see, the liquid is filling the cell. When the last gas disappears, we have all liquid. By continued heating to a temperature above the critical temperature, we enter the dense fluid region. We now slowly expand the fluid at a constant temperature of 100 degrees Fahrenheit. This is 10 degrees Fahrenheit above the critical temperature, so the expansion takes place without any formation of an interface. At the end of this expansion, we have such a high specific volume that the material in the cell is certainly what we would call a gas. To show that it is a gas, we cool it from 100 to 80 degrees Fahrenheit at constant volume. And when we reach a temperature of 85 degrees Fahrenheit, liquid begins to condense and slowly fills the bottom of the cell.
This process looks this way on the model and this way on the pressure temperature diagram, this way on the pressure volume diagram, and this way on the temperature volume diagram.
So far, we have been discussing behavior near the critical point. The other interesting point on this diagram is the triple point. For ethane, which we have been using, the triple point temperature is minus 300 degrees Fahrenheit, which is inconveniently low to use in this apparatus. So we will switch to tertiary butanol, which has a convenient triple point temperature of 79 degrees Fahrenheit. Water expands on freezing, which is why ice floats. This is very unusual. Most substances contract on freezing, which is why solid tertiary butanol, in equilibrium with liquid tertiary butanol, settles to the bottom of the container. For a substance which contracts on freezing, the triple point is the lowest temperature and the lowest pressure at which the liquid can exist in equilibrium. We may show this by compressing tertiary butanol at a temperature about 1 degree Fahrenheit above its triple point temperature. Here, as we decrease the volume at constant temperature, the gas slowly disappears, as it did with the ethane. The pressure is very low, about 1 psi. When all of the gas has disappeared and we continue to decrease the volume, the pressure rises rapidly because the liquid is only slightly compressible. Finally, we reach the pressure at which solid tertiary butanol begins to form, and the needle-like crystals grow out into the fluid. As this happens, the dark mercury at the bottom of the cell continues to rise, taking up the space vacated as the tertiary butanol shrinks upon freezing.
This process looks this way on the model, and this way on the pressure temperature diagram, this way on the pressure volume diagram, and this way on the temperature volume diagram. If we continued slowly raising the mercury level at this temperature, we would convert all the liquid to solid, and then the pressure would rise rapidly. However, this would take too long to do, even in accelerated motion. If we now lower the temperature below the triple point temperature and wait for the system to come to equilibrium, we will have all solid. Here we have frozen a tertiary butanol solid and are going to expand it at a temperature of 70 degrees Fahrenheit. At this temperature, below the triple point temperature, no liquid can exist. We expand it by withdrawing the mercury, and as you can see, the space between the mercury and the solid tertiary butanol fills with gas. If we continue to expand the system, the entire solid would transform to a gas. However, the density of the gas is very low. So to have completed this transformation with this amount of solid would have required a gas volume of 70 cubic feet, many times the volume of the equilibrium cell. This process looks this way on the model, and this way on the pressure temperature diagram, this way on the pressure volume diagram, and this way on the temperature volume diagram. We have seen that a single pure substance can exist in the form of solid, liquid, or gas, and that the conditions under which it takes up each of these forms depends on the pressure, temperature, and specific volume. These relations can be conveniently represented on a three-dimensional PVT surface or on its three two-dimensional projections. The most interesting places on this model are the critical state, where the liquid and gas become indistinguishable, and the triple point, where solid, liquid, and gas can coexist. A knowledge of these states is necessary to any understanding of thermodynamics, geological processes, or the world around us.